assessment framework, mediation. I'll be your host and going through this assessment framework for both paper 1 and paper 2 with you. And my name is Mr. MOHAPI TV. So to start off, it is important that all learners in the Free State have hard copies of the assessment frameworks. So we'll urge all teachers to print the assessment frameworks to the learners, that the learners must always refer to the assessment framework as they prepare for their June examination. So I will be going through both paper 1 and paper 2 assessment framework for June examination in the Free State province. So let us then begin with the paper 1 assessment framework for physical sciences. With physical sciences, these are the topics that are going to be assessed in our paper, and the mark distribution is given in the table, as you can see in your screens there. Firstly, learners must understand that we have about 4 knowledge areas in physical sciences paper 1. In fact, 3 knowledge areas that are going to be assessed in paper 1. That is your mechanics, wave, sound and light, and electricity and magnetism. So amongst the topics that fall under mechanics, we have Newton's laws, vertical projectile motion, momentum and impulse, work, energy, and power. The mark distribution for each of the topics under mechanics is given there, with Newton's laws being plus or minus 20, vertical projectile being plus or minus 27, and then momentum and impulse being plus or minus 25, and work, energy, and power being plus or minus 26 marks. This is what you will then expect your paper to come as when it comes to the different topics that fall under mechanics as the knowledge area. But you must also recognize that in the paper of 150, 98 marks will be based on mechanics. So it then says to us that the bulk of the marks in our June paper will be on mechanics. If a learner is to pass and get the distinctions, then most of the marks that they must get will be from mechanics. And then we have wave, sound and light, and the topic examined now in June is Doppler's effect. And then plus or minus 16 marks out of 150 will be coming from Doppler's effect. Then we have electricity and magnetism. About 36 marks of the 150 of the paper will be coming from electricity and magnetism. And electricity and magnetism includes electrostatics and electric circuits. And they have a share there of plus or minus 18 marks each. And then please note that the plus or minus means that it will not be exactly as given in the table here. It might be a little higher or a little smaller. But the total of the paper is 150 marks, and we are writing on the 22nd and the 19th. The total of the paper is 150 marks, and then it is going to be written for 3 hours. Yes, paper 1 will be written on the 19th of June. So that is but the structure and the topics that we must expect in our paper 1 June physical sciences. The distribution in terms of the cognitive levels is given as follows. We have cognitive level 1 questions where learners will be expected to recall and give an answer from recalling and remembering. Then such questions will constitute about 15% of the paper. We are talking about more or less 22 marks of the whole paper. And then understanding and comprehension, that is cognitive level number 2 questions, that will be approximately 35% of the paper. And then we have applications and analysis. That is then where we have a percentage close to 40%. We are talking about 60 marks out of 150. Yeah, we are talking about maybe 55 marks to 50, 52, 53 marks of the paper. And then we have evaluating and creating, that is 10% out of 150. That is what? About 15 marks of the paper will be what we'll then refer to as high order questions. So from this table, learners must then recognize, or you cannot fail because of the high order questions, because high order questions will only constitute 10% of the 150. So no learner can say they have failed because of high order questions. Even us as teachers, we need to train our learners on how to answer a question paper. A learner can't be stuck on one question of high order for the whole hour or 2 hours. A question that constitutes about 3 or 4 marks, then the learner is stuck there for an hour or 2 on a question that that costs about 5 marks or maybe 6 marks. So most of the questions will be on cognitive level 1 and cognitive level 2 and 3. Not that level 4 questions will not be there, and we are not saying learners must not write or attempt to answer high order questions. They must do, but most of the marks will come from lower level cognitive level questions. Even if you were to take cognitive level 1 and 2 questions, with those only, you can see that a learner can get 50% out of 150. So the first advice to the learners is that they need to ensure that they get cognitive level 1 and 2 questions. Those ones, no learner must miss. We focus on level 1 and 2 questions. You answer them first. That is one of the things that we'll talk to as we continue with the mediation of the assessment framework. But the target for all of our learners should be on cognitive level 1 and 2. Ensure that you get questions of level 1 and 2, and then we then improve the levels and the quality with cognitive level 3 and 4. But for a pass, level 1 and 2 questions should be given for all our learners. Then the skills that we need, because these are some of the things that our learners neglect. Remember, you can be asked practical skills in an examination. So you must know these practical skills. You must know these practical skills. Hence, it is important that we perform experiments in our schools and we write the worksheets. We get used to this questions. We are able to answer questions given in form. What are those things that we will be required to give or answer questions based on? Things like identifying the variables, and then from the variables being able to write an investigative question, from the variables being able to write a conclusion or a hypothesis. It is very, very important that whenever you are given a question in a form of an investigative question, know how to identify variables. After identifying variables, you must then be able to write an investigative question, hypothesis, and conclusion. And whenever you write a hypothesis or a conclusion, please note the phrasing is very, very important. But first, for you to be able to get the mark, we will then check if your variables are correct. If the variables are wrong, then the answer will be wrong. You will not get 2 marks. So the most important thing is to identify the variables. Then after identifying the variables, when it comes to the investigative question should always seek the relationship between your dependent and your independent variable. Then when it comes to your hypothesis and the conclusion, we start first by changing the independent variable, then the dependent variable will change. You can't change the dependent first and then you go to the independent variable. Whatever that you have identified as your independent variable must be the one that changes first, and then what you have identified as the dependent variable will then change after, because it depends on the changes made on the independent variable. That is very, very important. And then we must also identify the controlled variable. We must be able to list the apparatus that we use to conduct this experiment. All the prescribed experiments, any one of them can appear in a paper, and learners may be asked to identify the variables, the apparatus. So it is important that we conduct these experiments. It is important that we write the worksheets where we will be assessed on these skills that I am reading out to you. So the plan, the sequence of steps, you must be able to give details. After this is what happens. After this is what happens. After this is what happens. And then after that, you must also be able to tell us if an investigation is it a fair investigation or not. We know for a fair test, there should always be one independent variables. All other variables that can affect the dependent variable, that can influence the dependent variable, must be kept constant. But if you have more than one independent variable, then that test cannot be a fair test. So our learners must know, or if they are given to a question where they compare the investigations and they find where there are two independent variables or more than one independent variables, then it means that comparison or that test is not a fair test. For a fair test, there has to be one independent variable. That skill is very, very important, and you must have seen, especially my learners, from previous year's question papers, especially the recent papers, an investigative question is always there in a question paper. So that is what we are gravitating to, and learner, you must adapt to that, where there will be an investigative question somewhere in either paper 1 or paper 2 or in both papers. There might be, and then you must be able to deal with these things. And after that, you must be able to interpret the results. You must be able to tell us the trend, or from this is what I've seen. After conducting this experiment, it then means this is the relationship that we come up with, and then draw graphs, interpret all those graphs there, and then also perform calculations based on that. I've already talked about the conclusion and the calculations, and then you can also talk to whether the results are valid or not, or maybe account as to why the results are not reliable, or why is our hypothesis not achieved. What happened in the process of an investigation that led to maybe a law not being seen. For instance, we have an experiment that we do of conservation of linear momenta. Many a times we are unable to prove it practically, and then we need to then account for why is total momentum before not being equal to total momentum after. We must know all those reasons. Those are the practical skills, and these practical skills, remember, are applicable for both paper 1 and paper 2. So I thought that we start with them, and then we make learners aware that they may be asked an investigative question, and whenever they are asked for a question in a form of an investigative question, then these are the practical skills that they will need. So as they prepare for their junior examination, they should, or learners must take these things into cognizance and practice using them. Now getting to the concepts or the topics for paper 1. But before I talk to these topics, it is important that our learners, as I indicated earlier, whenever you get your question paper, please go through the question paper before you start writing. Please go through your question paper from question 1 up to the last question. Please do that. And as you go through your question paper, the first and the most important thing that you must do is to identify the questions that are cognitive level 1 and 2. Then you say for question 1, these are the questions that are cognitive level 1 and 2, and you start with those questions. Obviously, such questions will not require you to think a lot. So please start for each and every question with the questions that you will be able to get marks of. Do not start haphazardly. You go to question 1 and you see I am able to answer question 1.1, maybe 1.3, 1.5, and 1.7, and then you leave space for those that will require you to think maybe a little bit hard. Then you go to question 2, you do the same, you answer those that are cognitive level 1 and 2. You go to question 3, you do the same, question 4, you do the same, question 5, you do the same, question 6 and 7, and so on and so on. Then after having collected all the marks of cognitive level 1 and 2 for the whole paper, you can then come back and answer these other questions. What we do not want to see is for a learner to be stuck in question 2.4 of high order as an example. Then they are stuck on the question that costs 3 marks for 2 to 2.5 hours trying to solve this one question. One, you will waste your energy and you will waste your time. So please go through the question paper, identify the questions that you will be able to answer without thinking hard, and then answer those first. Then come back here and then go through the question paper. Because the target, remember what I said earlier, is for us to get cognitive level 1 and 2 questions. Then from cognitive level 1 and 2 questions, we'll then improve our marks with cognitive level number 3 and 4. But the first thing is the first hurdle is for us to get achievable marks, which are cognitive level 1 and 2. I hope our learners will practice the question, or rather the answering of the question paper like that. Secondly, it is important that our learners recognize we are not going to accept any definition if it is not given as it appears in the examination guideline. I hope by now each and every learner has got a copy of examination guideline per topic, and they know the definitions, the laws, and principles that are related to each and every topic. So it is then prudent for our learners to ensure that whenever they are asked to give a definition, a law, or a principle, they give it as it appears in the examination guideline. Nothing or no definition, principle, or law will be accepted if it is not the same as the one that appears in the examination guideline. So please, my learners, ensure that you know your definitions by heart. And how do we know these definitions? As you prepare for your examination, I take it that you'll do by topic. Maybe let's say you'll start first with Newton's laws as an example. Before you look at the previous year's question papers or practice questions, whatever that you may use, please look at the definitions. Read the definitions. Close the book. Then write them without looking at them. Then you mark yourself after that. Then you do the same. If you are not sure or there are some that you are still missing, again, read them. Close the book. Write. Mark yourself. Before you look at the long questions, please. That is very, very important to do. Know your definitions, and you do not know your definitions if you are unable to write it without looking at it. If you are unable to write it without looking at it, then it means it is not yet in your head. It is not yet part of your system. But I take it, or at this moment, no learner doesn't know their definitions. Then that will help us with the 50% of level 1 and level 2. So please do it like that, and I can guarantee you no learner will lose marks on the definitions. That is the second thing. The third thing, when a question comes, especially those ones that will require you to explain why did you choose greater than, smaller than, or no effect. We know such questions. They will always be there. Whenever a question such as that comes, very, very important, just look at what, or rather identify the variables. I always say, let us identify the variables. What will be the variable? We will be told, hooray, now, for an example, an angle has been increased. What will then happen to the kinetic frictional force, as an example? Or they will say the velocity has been decreased. What will happen to momentum? Such questions will always be there. And it is part of physical sciences. That is where the application part comes in, where we apply now these principles, the formulas, and the laws that we have in physical sciences. So whenever such a question comes, please identify the independent variable. What will be the independent variable? The independent variable will always be this variable that they say it is changing. They will tell you this is what changes. Then from what changes, you say, okay, this is my independent variable and this is how it changes. If they say if the mass has increased to whatever value, what will be the effect of that change in mass on momentum? Then change in mass will be your independent variable. And they want to check what happens to the momentum. Then momentum becomes your dependent variable. So you will then have your independent variable and you have your dependent variable, which is the variable that they are looking for or the effect on. Then you take this dependent variable and the independent variable, you go to your formula sheet and you identify a formula that relates the two variables. Then you will then be able to see, okay, we have this formula that relates my independent variable and my dependent variable. And then they say when mass increases, what happens to momentum? Then you will then be able to say, okay, if mass increases, according to formula P is equals to mv, then momentum will also increase. But because we are using a formula, yes, it is a correct formula that relates the two variables that you have identified. But in this formula, I have this other variable, which is part of the formula. You can't wish it away. Then it then means, or this other variable, or rather, yes, this other variable, which in the case of momentum and mass formula, it will be the speed or velocity. Then it must be kept constant. So in your explanation, whenever you use the formula to relate the two variables, and that formula has got other variables, then these other variables must be kept constant. That is the principle that we use whenever we explain the changes, or the effect on other variables because of the changes that were made on the other variables. So it is important that you do it like that, and I can guarantee you those questions that require you to explain, you will never get them wrong. Those are some of the things that I wanted to highlight before we get to the topics. And these are applicable for each and every question, because these explanation questions can come up anywhere. These explanation questions will come up anyway. And then when it comes to the issues of a graph, it is important, especially in paper 1, that we relate these graphs with mathematics that we know. We know a straight line graph has a form of y is equals to mx plus c. That is what we know. So whenever you are given a straight line graph, some of the questions will come in a form of a straight line. So we have our variables in physical sciences, yes, but all straight line graphs have the form, which is y is equals to mx plus c. Then and we know from that, already the y in the formula, yeah, y is equals to mx plus c talks to the y input, which will be the one on the vertical axis, and the x talks to the horizontal, or rather variable, or the variable in the x-axis or the horizontal axis. Then you take those two variables, you relate them with a formula, and from that formula, you rearrange that formula. You look for the formula that has got the two variables that were used to draw a graph. And you then rearrange that formula so that that formula takes a form or a format of y is equals to mx plus c. Then from there, you'll be able to see, okay, if I rearrange this formula that relates the two variables, I can see this is my y, this is my x, and whatever that is a coefficient of my x will be what? Will be my gradient, and plus whatever on the other side, that is your c. Whatever that I add on this side, according to the rearrangement that I've done on the formula, will be my y-intercept. That is how we interpret, especially the straight line graphs. So please, learn those things, and always whenever you deal with the graphs, relate mathematical skills to the interpretation of graphs. And this, I said, it is applicable for both paper 1 and paper 2, and you'll be able to, but more on paper 1. Then if you master that skill, I can guarantee you that graphs will never be a problem to you. Whenever you are asked to identify the gradient of a graph that is given to you, then you rearrange that formula to be in the form of y is equal to mx plus c. Then whatever comes as a coefficient of your x, that will be your gradient. That is your m's. So from there, you will then be able to tell us, oh, this is my gradient. And you'll be asked to use that gradient maybe to solve the questions. So those are some of the things that I wanted to share with you before we get to the topics. Now getting to the topics, remember we said we are going to have mechanics, and mechanics all in all will constitute about 98 marks. And most of the marks on paper 1 will obviously be from where? From mechanics. We have Newton's laws. And remember, Newton's laws is a topic that we did in grade 11. So please go on and practice questions on Newton's laws. Everything on Newton's laws. But the common mistakes that we have realized when it comes to the definitions, I indicated, if it is not as it is given in the examination guideline, we are not going to give it. So please learn your definitions and take them as they appear in the examination guideline. Exactly as they are. We do not interpret the definitions. If you are asked to give a definition, give it as it appears in the examination guideline. That's it. Unless you are asked to explain or whatever, then you will explain. But when they say state this definition, or give the definition, define, state this principle, you give it as it appears in the examination guideline. That is very, very important. Then the other mistake that many of our learners make is on the drawing of free body diagrams. Please learn the rules of drawing the free body diagram. One, if you draw a free body diagram, there must be a dot. There must be a dot. There can't be just a point where arrows meet. No. There must be a dot, and that dot must be visible. I'm not saying you should draw a big thing that will fill the page, but it must be visible. We must be able to see that a dot which represents an object is given there. And whenever we draw the forces or represent the forces must touch the dot, pointing away from the dot in the direction of the force. Forces must be attached to a dot, and they must be pointing away from the dot in the direction of the force. If the force is going to the right, then the force, or rather the arrow, must be pointing to the right, touching the dot. If it is not touching the dot, then we are going to subtract 1. So all the forces must touch the dot. All the forces represented by arrows must touch the dot. And also, we have acceptable labels that must be given. If an arrow is drawn or is shown without a symbol of the force, then that is not a force. We do not recognize that to be a force. You will not get a mark. Arrow goes with a symbol. And not only straight lines, those lines must have arrows to indicate direction. If you only have lines there, you are not going to get a mark. Those are some of the things that our learners lose marks on, because they will then not draw straight lines. They will then sometimes have lines that do not touch the dot. If it does not touch the dot, it is wrong. It is not acting on that object. That is what it means. And they must be straight line in the direction of the force, but pointing away from the object. That is the most important thing when it comes to free body diagrams. And you must know the correct labels or acceptable labels for our forces. For instance, applied force will accept if a learner represents an applied force using a capital letter F. And we must be able to differentiate, between a capital letter F and a small letter f. Obviously, a capital letter F will have a square at the top there. But a small letter f will be kept like. So please, let us see the difference between a capital letter F and a small letter f. So for applied force, we have acceptable labels. We have capital letter F. We have the magnitude of that applied force. Or you have F applied, not FF. If you write FF, we are not going to give you the mark there. Or F subscript capital letter A. If you say F small letter A as a subscript, we are not going to give it to you. So please be aware of such things. If you do not adhere to these acceptable labels, then we are not going to give you marks. So ensure that you know for each and every type of a force the acceptable labels to represent all these forces. I was making an example with the applied force. You must then go and check for tension, normal force, frictional force, weight, and the likes. Please. And then when it comes to calculations, remember, we must take the formulas as they appear in the formula sheet. Some of these formulas, they have subscripts. Some have superscripts. So we must see that if we are going to write Fs max, we must see F subscript S and superscript max at the top is equals to mu S. We must see that subscript S there multiplied by normal force, capital letter N, or F, capital letter N, not small letter n. We must see those subscripts when you write the formula. Let us take the formulas as they appear in the formula sheet, please. And note, you will not get a mark if you write a formula without substitution. If you give a formula and then you do not substitute into the formula, or there is no attempt to substitute into the formula, then the mark for the formula will be forfeited. So you write the formula and then you substitute into the formula. Is then when we will get a what? A 1 mark. If you do not do that, then you will not get that mark, a formula. So please be careful. Writing of the formula without substitution doesn't have any marks. So let us take the formula as it appears from as it appears in the formula sheet. Then there is this tendency of our learners of taking normal force to always be equal to gravitational force. Remember, we have different situations for our object. There will be instances given where your normal force will be equal to your gravitational force. And there are instances where our normal force is equals to gravitational force minus the vertical components of the applied force. We have instances where normal force is equal to normal force is equal to gravitational force plus the vertical components. We have instances where normal force will be equal to the perpendicular component of the weight. We have instances also where normal force will be equal to perpendicular component minus the vertical component of the applied force. And normal force being equals to the perpendicular components of the gravitational force plus the vertical component of the force. And we have some instances whereby we will have the force being applied against an object. And in that case, if a force is applied against an object, then normal force will be equal to the applied force plus the gravitational force. So we must know all these different situations, for we do not know which one is going to appear in June. So as you practice, please ensure that you master all these different scenarios or situations wherein a normal force may be asked, and we must know all of them and practice them. Please, normal force is not always equal to weight. Yes, there are instances where normal force is equal to weight, and we must know all of them. Then we talked to the relationships where learners will be told, this is changed, and when this is changed, what will happen to this? We said you should take this one that is changed as your independent variable, and whatever that they are looking for the effect on as your dependent variable, then look for the formula that relates the two. And whenever you look for the formula that relates the two, and that formula appears to have other variables in, these other variables will then be kept constant as you then tell us the relationship between the two variables. That is the standard whenever we answer this question. And always try to use point form to explain. For instance, you'll say momentum, or rather the mass is increased at point number 1. That is your independent variable. There's no mark for that. Then you go to the second point. According to this formula, P is equals to mv. For constant V, when mass increases, then momentum also increases. Then you get your 2 marks from there. That is how we should always answer these questions that requires us to give explanations. Very, very important. So that is what we talk to when we say explaining the relationship between variables. You look for what is being changed, and then you look for what variable are they looking for an effect on. Then you go and look for the formula that relates the two variables, and then you work them as I've explained. So please look at those things. Then when it comes to vertical projectile motion, the definition of vertical projectile motion, I've already said, if it is not from the examination guideline, it is wrong. But the common mistake that our learners make is to confuse free fall with projectile. Remember, free fall is the motion, and projectile is an object. So this one, free fall is the motion under the influence of gravitational force only. This one is an object moving under the influence of gravitational force only. So please check that difference between the two. Then the other thing is the learners replacing gravitational force with gravity. Gravitational force is a force. Gravity is a field. So we can't replace gravitational force with what? With gravity. If you do that, you will lose 2 marks. We will not accept the replacement of gravitational force with what? With gravity. So please be careful when it comes to the definition. Yeah, free fall and a projectile. Then we have graph interpretation. There will be instances whereby a question will come in a form of a graph. And when it comes to vertical projectile motion, we have position versus time graph. We also have velocity versus time graph. We also have acceleration versus time graph. We must be able to interpret those graphs when a question is asked in a form of an in a form of a graph interpretation. And when it comes to velocity versus time graph, learners must note where the graph starts. I'm talking here of velocity versus time graph. Where the graph starts, where time is equals to 0, that is your initial velocity. So you must then look at the graph and say, okay, this graph is starting at this point, or rather the 0. When time is equal to 0, then velocity is this much. Then that then becomes your what? Your initial velocity. Then you work with that initial velocity throughout, because we know amongst or in all those 4 equations of motions, initial velocity is always there. It's one variable that appears in all the equations of motion, which then means it is the most important variable when it comes to equations of motion, because when it appears, you look at all those formulas, the equations of motion, initial velocity is there. How then do we identify an initial velocity from a velocity versus time graph, where the graph starts when time is equal to 0? That is your initial velocity. The value of velocity there will be your initial velocity. Then you work it from there. Then I'm telling you, you'll be able to get whatever answer there, or rather, you will be able to do whatever calculation that you may be asked to do. And then I've already indicated that whenever you deal with straight line graphs, because in terms of the shape, the velocity versus time graph for a vertical projectile motion or a projectile will always be a straight line graph. And a straight line graph, if you then use that formula, Vf is equal to Vi plus A delta T, you'll then realize, okay, Vf is the changes in velocity, that is my y input. And then T is my x input, because it will be on the x-axis. Then A, which is the acceleration, must be my what? My gradient. And my y-intercept will be my what? My initial velocity. That is how we interpret these graphs using physics formulas. If you rearrange that formula, Vf is equal to Vi plus A delta T, you rearrange it, you put it nicely to be in a form of y is equal to mx plus c. Then you'll see from there, or my y is Vf, my m is A, my x is delta T, and my y-intercept, which is c, it will be my what? Will be my initial velocity. That is what I was talking about when I was referring to the interpretation of graphs using mathematical skills. So please do that. And then you look at the direction from the graph. If you have identified my initial velocity, then you check where is your initial velocity drawn. If it is drawn on the positive axis, it means the initial motion of the object is taken as positive. If the initial velocity is drawn, or the graph starts on the negative axis, then it means the initial motion of my object has been taken as what? As negative. It is very, very important, because sometimes you will not be told the choice of direction, but you must find it from the what? From the graph. If the graph is given to you, and my initial velocity, or rather the graph starts in the positive axis, then it means the initial motion of the object is taken as positive. If the graph starts in the negative axis, then it means that the initial motion of the object is taken as negative. Then you check. That is number one. Okay, if the object, we are told, or it is moving upwards and that the graph starts in the positive axis, it means upwards has been taken as positive. If we are told in a statement of the object is thrown, as an example, is thrown down, and the graph is thrown on the positive axis or starts in the positive axis, my initial velocity is in the positive axis, it means those people have taken downwards as what? As positive, and then we use that choice of direction to answer our question. Because whenever a velocity versus time graph, or rather any graph is given to you, it means direction has been chosen for you, and then you must follow that. That is very, very important. And then having done that, we must also remember that especially for a projectile or free fall, our acceleration is 9.8, which is always downwards. It does not change direction. It will always be positive if downwards is taken as positive. It will always be negative if upward is taken as positive. So please note that the gravitational acceleration does not change direction. Because it does not change direction, it depends, or the sign of it will depend on the choice of direction. If we say up is positive, gravitational acceleration will be used as a negative 9.8 in a what? In a calculation. But if we say down is positive, then gravitational acceleration will be used as positive 9.8 in the calculation. That is very, very important. And then these other ones, so now they will then take their side from the interpretation of the motion. Like for instance, if we go up and we have taken up as positive, all upwards velocities will be positive. And then whenever object goes down, then the negative velocities, or the velocities when the object goes down, will be negative. That is what I wanted to highlight when it comes to vertical projectile motion. Another thing is a situation whereby we will be asked to find any variable without using equations of motion. When a question clearly states that without using equations of motion, it means that we must use the properties of the graph to find whatever that they want. We know for a velocity versus time graph, the area under the graph will represent the displacement. The area under the graph of velocity versus time graph will represent the displacement. We know the gradient of that graph will represent what? The acceleration. So if a question comes and says without equations of motion, then do not use equations of motion. Please answer that question using the properties of the graph, such as your what? Your area under the graph and the gradient of the graph. That is the example that we made here. Then when using equations of motion, please copy the formula as it appears. That small f there for final velocity is very, very important. That small I there is very, very important. So please write the formula as it appears in the formula sheet. And remember, if you write the formula and you do not substitute, no mark. You must at least substitute. And whenever you are asked to calculate final velocity, obviously the formula that we are going to mark is the formula that you are going to use to find final velocity. You can't use the formula without final velocity to find final velocity. So you need to check what is it that they said I must calculate. Then the applicable formula for that will be the formula that has got that variable that you are asked to calculate. So it is important that you do that as I am saying, because we have 4 formulas here. Not all of them will be applicable for each and every calculation. You must check what is it that I'm asked to calculate, then use that formula, or rather a formula that contains that variable that you are asked to calculate. And it is important that we break the motion into portions. How so? We will have instances whereby you'll take this part of the motion maybe from point of projection to the maximum height. Then if you do that, then you will say wherever I start is my initial point. So velocity at that point will be my initial velocity. And wherever I end is my final point. Therefore, velocity at that point will be the final velocity. So whenever you deal with motion or equations of motion, take motion parts by break it into parts. Where you start is your initial point, and then the velocity you have there will be my initial velocity. Where you end will be my final point, and velocity you have there will be your final velocity. And then your time will be taken from the point, initial point, to the final point. Because there are instances where you'll have a lot of times, but maybe you are asked for to analyze a certain portion of the motion. Then identify your initial point and your final point, and then work from there. That is very, very important that we break the motion into parts. Before I forget and pass that part of graphs, whenever a graph is drawn, especially the velocity versus time graph, because that is where many of our learners struggle when it comes to interpretation. If a graph starts, we said where it starts is our initial velocity. It then indicates where from initial velocity, that is the first part of the motion. If from initial velocity your graph goes to the time axis, we know where it cuts the time axis, that is your maximum height. Then it means that if the graph from initial velocity goes to the time axis, then the initial motion of that object is an upward motion. But if your graph from initial velocity goes to, it doesn't go to the time axis, doesn't go to the maximum height where velocity is equal to 0, then it means that the initial motion of that object is a downward motion. So we must be able to differentiate between the two. You look at the graph and then you check, oh, the first part of the graph goes away from the time axis. Then it means that this object, its initial motion was downwards. But if it goes towards the time axis, then it means the initial motion of the object was an upward motion. Then you choose the direction as I indicated earlier. That is very, very important interpretation of the object, because we know or whenever an object goes down, especially a projectile, whenever it goes down, its velocity must increase. But whenever it goes up, its velocity will decrease. So you must be able to identify such things. It goes up, velocity decreases up until it is 0 at the maximum height. It goes down, velocity increases up until the maximum velocity on the ground. Those are some of the things that we must be able to identify whenever we are given a graph to interpret. And then whenever you draw the graphs of motion, very, very important. When we draw the graphs of motion, firstly, let us talk to the shape of the three graphs that we listed earlier. Velocity versus time graph is a straight line graph with a what? With a gradient. Meaning it must have a steepness, it must have a steep somewhere. It can't be a horizontal line. It's a straight line graph with what? With a gradient. Position versus time graph, that is y versus time. It will always take a parabolic-like shape. It must take the parabolic-like shape, always. So at least when it comes to the shape of the graph, let us not get those wrong. Straight line graph for velocity versus time graph with a gradient. Parabolic shape, if you do not understand what parabolic means, we know in mathematics how to draw a parabola, that is ax squared plus bx plus c. That kind of a graph like. That is how your graph should look like. It might be part, but at least the shape must be like that. When it comes to acceleration versus time graph, for a projectile, we know that this one will be just a straight line, a constant line, zero gradient. Why? Because for a projectile, the acceleration is constant. It does not change. It will be 9,8 throughout. And also its direction does not change. So at least let us get the shapes of the three types of graphs correct. Let us ensure that the shapes are correct. And then you put in your labels. I indicated when it comes to velocity versus time graph for it, where the graph starts is your initial velocity. So if you are to draw a graph, you have velocity versus time graph, then the graph must start at initial velocity. And then you count the time. If the object is going up, then where velocity is equal to 0 must be equal to the time it took the object to move from wherever it is, or rather from its point of projection to the maximum height. That will be the time. Then it continues like that. Those are things that you must note. When it comes to a parabolic shape, please take note of the reference point, because you will always be told, or take this as your reference point. They might say take the ground as the reference point, or take the point of projection if it is then thrown from somewhere above the ground. They say take the point of projection as your reference point. Then you work from there. For my graph, this parabolic shape kind of graph will start from that. And then note, if you have taken upwards as positive, then whatever that is above my reference point must be positive. And whatever that is below my reference point must be drawn in the negative axis. That is how we use the reference point. You take the reference point, and if up is positive, or rather you have taken up as positive, whatever displacement that is above my point of projection, or my reference point, I mean, then it then means, or it will be drawn on the positive axis in that graph, your position versus time graph. And whatever that is below the reference point will then be drawn in the negative axis. That is how you should practice your graphs. And the opposite will obviously be true. If down is taken as positive, then the opposite happens. Whatever that is above the reference point will be drawn in the negative axis. And whatever that is below my reference point will be drawn in the positive axis. So I know sometimes we use words like, you draw this one, yeah, upwards as positive, and if you are asked with downwards as positive, then you just flip it. Then you get your correct answer. But in principle, we use reference point, displacement above, if we have taken upwards as positive, is positive. Displacement below the reference point will be taken as what? As negative. That is the principle. And the opposite of that is also true. That is what you need to know when it comes to the drawing of graphs of motion. Okay, and also remember to integrate all these topics of mechanics into one. For instance, you may be asked a question on momentum in a projectile motion question. There's nothing wrong. Remember, these are all part of mechanics family. So in here, in momentum, you may be asked vertical projectile or motion type of a question, or force type of question. All these are related. So don't be surprised in a question you have vertical projectile motion, then you are asked about momentum, or rather impulse, or you are asked about elastic and inelastic collisions. They are part of one family. So such questions may come. And when you have a question of a bouncing ball, obviously the issue of a force will definitely be there. And we know at the point of contact where the object will be bouncing, there will be a change in velocity. The common mistake with our learners is they confuse the initial velocity and the final velocity. if you are asked to calculate the impulse at the point of contact, you concentrate on the changes in velocity at that point of contact. It will then mean the velocity with which the object hits the ground with is your initial velocity. And the velocity with which the object leaves the ground with is your final velocity. So we look at the changes in velocity at that point of what? Of contact. So if a question or it is incorporated of impulse into a bouncing ball of vertical projectile motion, please take that into cognizance. For the one the object hits the ground with is my initial velocity. The one the object leaves with is my final velocity. I'm here referring to that question, or rather that formula, F net delta T is equals to change in momentum. We know when you expand change in momentum, it's mass into final velocity minus initial velocity. So this final velocity and initial velocity that I'm referring to, or rather this change in velocity, it is the change right there at the point of contact, not anywhere else. Because especially in a bouncing ball, you might have a lot of velocities there. When you are to apply this formula, maybe you are asked to calculate the force that the ground exerts on an object as it goes up. Then you must then talk to F net is equals to change in P over change in T. You concentrate on the point of contact. For initial, the one it hits with. Final, the one it leaves with. Please take that into consideration as you practice. And then we can then move on to momentum and impulse. I've already talked about the laws and the definitions, calculations. Here, the symbol for sigma, guys. Sigma, let it be clear. Some of our learners will write an E instead of a sigma. Then that is not a sigma. If you write an E instead of a sigma, then it is wrong. And I'm going to say something that might seem very harsh, but it is correct science. If the principle is wrong, then we are not allowed to mark any further. So please be careful on how you write symbols, because symbols to us, they talk. That is how we talk in physical sciences. We use symbols. When you say sum, it must be a sigma, a correct sigma that we know. So if you are unable to write the correct sigma, your sigma is like an E, please go and correct it and practice to write the correct sigma there. And then it will be sigma PI is equals to sigma PF. Many of our learners will omit the I and the F. If we just write sigma P is equals to sigma P, to us you have not said anything. You have not written a principle correctly. So please be careful of those smaller things. And then the omission of subscripts. If you then choose to write your formula as MV plus MV is equals to MV plus MV, then we are not going to accept it. So please be careful. Be careful on how you answer this question. Or rather write this formulas. So the principle is when you write the formula for different objects, those objects must be symbolized differently. You are dealing with object A and object B. Then the mass of object A and the mass of object B must be symbolized differently. You can't say M and then M while you are symbolizing different objects. Again, it will be MA and then MB. Then we know MA stands for the mass of object A. MB stands for the mass of object B. And then you have some will write V, and then on the other side also write V. When you have two different velocities for two different objects. This one, it will be VI1. This one will be VI2. We know that is the initial velocity of object 1, and then this one is an initial velocity of object 2. Also, you have final velocity and initial velocity. The two must be symbolized differently. So those are some smaller things that cost our learners marks. So please be careful that you give the correct subscripts to symbolize different objects. If the variables, the variables are different, they must be symbolized differently. But if you do not symbolize them differently, then it means you are not going to get any mark for the formula. Then when it comes to the type of collisions, we have elastic and inelastic. We must know the difference between the two. But whenever we are to prove whether the collision is elastic or inelastic, please do not start by equating the two total kinetic energies. You must first calculate total kinetic energy before on the side. Then calculate total kinetic energy after on the side. Before you equate them, you can't start by saying total kinetic energy before is equals to total kinetic energy after. Once you do that, you then say, or rather you have already concluded that the collision is elastic. Again, one of the properties of an elastic collision is that the total kinetic energy before collision is equals to total kinetic energy after collision. So once you start by doing that, then to us, you say the collision is elastic. There's no need for us to even look at your calculation any further. You have already concluded, you have already answered our question. So whenever we prove, please calculate total before collision aside. Calculate total after collision aside. Then after finding the values, you then compare. You then tell us if they are equal or not. You can then say total before is not equal to total after. Then once you have done that, you can then conclude to say the collision is elastic or the collision is inelastic. Those are smaller things that learners do, but then they lead to them losing marks. So please be careful whenever it comes to this issue of proving. Then the application, I've already talked to it in terms of the calculations, but there is this one that talks to the impulse momentum formula or momentum impulse theorem, where learners must know the importance of airbags. Learners must know the importance of someone who's landing on the ground. Why do they bend their knees and all those things, or the impact why a golfer will then swing first before they hit the ball. Why? All those examples. Other examples will be the arrestor beds. Why do we have arrestor beds in our roads? All those things. You must be able to use momentum impulse theorem to explain the importance of such things. And as I indicated earlier, when we explain point by point, please tell us, for this changes this in this way. According to this formula, keeping this constant, when this changes in this way, this is what will happen to this one. That is how we explain it using physics principles or laws. If you do not do that, then you lose marks. If you do not refer to any law or formula in physical sciences, then to us, you have not said anything. So please be careful. Then, when it comes to work, energy, and power, the laws, I've already talked about it. And I think I've also talked to the calculations, but the main problem when it comes to work, energy, and power, when it comes to the calculations, is that learners confuse F net and W net. Net work done and F net of net force, totally different things. Net force talks to the sum of the forces acting on an forces acting on an object. Net work done to confuse the two. When you talk net done, it will be by applied force, by gravitational force. Those are forces acting on an object. When you talk to the net force, it will be applied force, not work done by applied force. Applied force plus frictional force plus gravitational force. if those are the forces acting on an object. So please, the fusion of the of the network done and between the two. And then when it comes to conservative and non-conservative, the number of which that is dependent on the force that is independent, for which work done is an or dependent on the partaking. Learners, in many a times, they will omit that part of the force for which work done. They just say the force that is on the path taken or the force that is independent of the path taken. And remember what I said earlier, if it is not as it in the formula in the examination guideline, it is wrong. So that is what comes to the issue of definitions. But with the non-conservative forces, when we use that formula, W and C is equal to change in kinetic energy plus change in potential energy. It is not, I know many times you'll find that the work done by non-conservative forces is equal to work done by friction. But it is not always the case. You need to know of conservative and non. Work done by non-conservative force will then mean the work done by all non-conservative forces acting on an object. If it's for friction there and tension in some instances, then it means work tension plus work done by friction. Many of our learners tend to think that work done by non-conservative forces will be work by friction. It depends on the situation. Yes, when friction, the force acting on an object, that will be equal to work done by friction. But if you have other non-conservative forces acting on an object, then they need to be included in that far. When it comes to the application, we must be able to differentiate between frictionless surface and rough surface. We know the whole in an isolated. Then when given a situation, be able to identify. But this part is isolated. Then the principle of mechanical energy is applicable. But from here to there, the system is not isolated. The external forces or the external forces is not equal. These are some of the things that must be done when it comes to the application. And we know the energy principles that we have. When a question says using energy principles only, the energy principles that they will be referring to is work done by non-conservative forces and the principle of conservation of mechanical energy. When it comes to principle of conservation of mechanical energy, you must know the relationship. You know, as the object goes down, starts from zero, gravitational potential energy decreases, but kinetic energy increases. On the ground, we know kinetic energy is maximum, but gravitational potential energy on the ground is equal to what? Zero. And the sum of the two in an isolated system will always give us what? Will always give us the mechanical energy. Those are some of the things that we need to make awareness aware of. But when will the object lose energy? When will it aim? In that instance, the object or the energy just changed from one form to the other form. But as a whole, the energy is not lost in the system. But there are instances where an object will lose energy. When is that? When we have the presence of non-conservative forces. So we need to make our learners aware of those things. But once we have non-conservative forces, then the system is going to lose energy. And because it loses energy, that will then affect your speed of the object. And we make our learners aware of such things. That is mechanics. That is where we will end with mechanics. I'll end in the interest of time, pass on to stating. I've already talked to stating. When it comes to in this question, please write the formula as it appears in the formula sheet with the plus and the minus. Write it as it appears in the formula sheet with the plus and the minus. Please do that. And then we know, for whenever we have an object, or rather two objects or whatever variables, I don't want to call them variables. Let's say you have a person and a car, and they want to demonstrate the Doppler effect. For our syllabus, we are not going to have a situation where both of them are moving at the same time. There will be one that is moving and the other one will be stationary. Then we check this one that is moving as to whether it is moving towards or it is moving away. That will then give us the sign to choose in the formula. If what is moving is moving to, whether it is the listener or the source, it is moving towards, otherwise, or away from the stationary one. Very, and that will tell us how then do we interpret the signs in the formula. Whatever that is moving, if it is moving towards, we know. On top, we'll have positive. And below, we'll have what? Negative. If whatever that is moving away from the listener or the source, whatever that is moving, if it is moving away, then we know on top we'll have negative and below we'll have what? Positive. Those are some of the things that we must know. And then from that interpretation, we substitute and then we get the marks. But we must also be able to relate the frequency and the wavelength. Remember, sound is a wave. So the wave formula is very, very important. That V is equals to frequency multiplied by lambda. Very, very important. But here we are talking of sound. Then it means the V there is the speed of what? Of sound. So because V is the speed of sound, it then means the speed of sound in the medium that is given to you will be the value that you substitute here. This V in this formula here, this V in the formula here is not the velocity of either the source or the listener, but it is the speed of sound in the media. So please substitute that speed of sound here. It is sometimes 340, sometimes it is 343, and all those things. Please substitute it there, not the speed of the listener or the source. Many of our learners make a mistake here. And we know the relationship between the frequency and the wavelength. We know they are inversely proportional. If frequency or rather wavelength increases, then it means frequency decreases. We know that relationship and we right. Because I asked giving up frequency, but giving up wave frequency, the relation proportional. Then we have the shifting. We know for our syllabus we'll be asked to explain using Doppler's effect the expansion of the universe. It's part of our syllabus. We must be able to do that. So the red shift and the blue shift, very, very important that we know how to interpret those things. But in our explanation, we must talk to the shifting, especially when you are given the spectra there. You must talk to the shifting of the spectral lines. You will see where from one spectrum to the other spectrum, these spectral lines, the lines in between, have shifted maybe towards the end. In fact, for expansion of the universe, they must shift towards the red end. Then in your explanation, you must say the spectral line shift to the red end. And what is the red end? Red end is the end of longer wavelength and smaller frequency. And we know, according to Doppler's effect, when it means whatever that is moving away. So some of the things that we must be able to talk to. And by scientists, the universe is expanding. The spectral lines shift toward the red end of the spectrum, and we know the red end is the end of longer wavelengths. Longer wavelengths, relationship that we talk, smaller frequency. According to Doppler's effect, detected frequency is smaller. It means whatever that is moving away from. Those learners to give us when they explain redshift. That is basically what we will be expecting from our learners when it comes to Doppler's effect. I think that is what I wanted to highlight when it comes to Doppler's effect. We can then move on to electricity and magnetism. For electricity and magnetism, that is where we'll then have electrostatics and electric circuits. Here, I know the two topics were dealt with in grade 11. We must go and revise these things. They will be there on the 19th. So please go and study your electrostatics and electric circuits. When it comes to electrostatics, definitions, same as I've stated earlier. The issue is with drawing of the electric field patterns. Many of our learners lose marks when they have to draw the electric field patterns. Remember, if an object or a sphere is standing alone, does not interact with any other sphere, or it is a charge alone, not interacting with any other charge, then it means we will not have the field lines bending. The field lines will only bend if there is an interaction with other charges or with other spheres. So if you are asked to draw a field line pattern, electric field pattern of one charge or one sphere, whatever it may be, if it is one, just one, then it means we will draw it with what? With straight lines. And whenever you draw, ensure that you use straight lines. And those straight lines of yours must touch the object or the sphere or the charge. They must not end somewhere in the air. They must touch the charge or the sphere. And ensure that none of them, if you are going to draw a big circle there, none of these field lines goes into the charge. We must not have field lines passing into the charge. So please draw them as I'm explaining, straight lines, all of them touching, none of them passing into. And they must all have what? Arrows to indicate the direction of the electric field. We know for a positive charge, the field lines will point away from the charge. But for a negative charge, they will point towards the charge. That is how we draw the field line pattern. But if you have two interacting objects and you are asked to draw air charges, and you are asked to draw in the electric field pattern due to the two charges, because now you have two charges there, then in that case, you will have some of those field lines bending. Because of what? Because of the interaction between the two charges. When it is alone, no bending, straight lines are only. But if you have two and you want to have a resultant field pattern due to two charges, then field lines must what? Must bend. And we know if we have positive and negative, into the negative, they must go in. The field lines must bend in the negative, they must bend in. But for a negative, for a positive charge, they must bend outwards. They must bend outwards. And then we'll only have those that are directly opposite the charges. Those are the only ones that will then be straight. But all other field lines inside or rather in between the charges and outside the charges, they must bend, except for those that are directly opposite the charges. Those that are directly opposite the charges, then those ones can be straight. But all the other ones, they must bend. For a negative charge, they bend towards the charge. For a positive charge, they bend away from the charge. That is how we draw the electric field patterns. And you must also do when you have both positive and positive or negative and negative. That is how we are supposed to draw the field lines. And then when it comes to the calculations, please, even if you are not asked to draw it, but draw the free body diagram. Again, we are dealing with a force here. Then it means the issue of free body diagram becomes important, because it is from the free body diagram that we will be able to determine the direction of force. The direction of the force is determined using the free body diagram. So how do you use the free body diagram? It will be the force that charge A exert on charge B. A carry on is the one that experiences a force. Then we look at it and we say, this B, in which direction will it go because of A? Then the force that A exert on B will be in that direction. So we draw a free body diagram to determine the direction of the forces. Even if we are not asked to do it, we must draw the free body diagram, because that is where we get the direction of the forces. Then you'll be able to find your net force and the likes. Same with the issue of electric field. We must draw the vector diagram to determine the direction of the force, because in the formula, the negative, we are not supposed to substitute. Remember, the law says the magnitude of the charges. We are only interested in the magnitude, but those signs will help us with what? With the direction when we draw the free body diagram, because they will tell us as to whether they repel each other or they attract each other. But that is where they end, and then when we substitute into the formula, we only substitute the magnitudes. So please draw the vector diagram for electric fields, free body diagram for forces, electrostatic forces. That is how you determine the direction when you deal with calculations of electrostatics. The conversions. Sometimes you'll be told, or this charge has got a magnitude of 2 nanocoulomb. Those nanos, we must know how to convert them to what? To coulombs. Those millicoulombs, those microcoulombs and the likes, we must be able to convert from those to what? To coulombs. Please, it will not be always the case where these charges are given in coulombs. Sometimes they are given in such conversions of nano and micro and milli and the likes. We must know how to move. Same with the distance. Our SI unit for the distance is meters, but sometimes the distance can be given in millimeters. Sometimes it can be given in centimeters and the likes, and then will be then expected to convert it to meters. Let us practice those things and be able to get the marks. I think this is one of the topics where many of our learners can get a lot of marks. And don't forget the formula, especially the units of electric field, is Newton per coulomb. So that -1 at the top there is important. Let us not forget to put the negative there. Then with electric circuits, formula, we have stated it. But before we get to the calculations, we need to be able to give the definition of EMF. Yes, that will give as given in the examination guideline. But sometimes we are asked to explain instead of define the EMF. If we are told an EMF of this battery is 24 volts, I'm just making an example. Babari, explain what does it mean that the EMF is equal to 24 volts. There they do not ask you to give a definition, but they want you to explain what does 24 volts EMF mean. Again, 24 volts EMF means that the battery can supply a maximum of 24 joules per coulomb of a charge that passes through it. That is you now explaining what 24 volts EMF mean. So if a question comes and says, explain this EMF, then you must be able to explain it like I've just said. You are told already, this battery has an EMF of 12 volts. They don't ask you to define what EMF is. They say, explain the meaning of 12 volt EMF. Then your explanation will be, this battery can supply a maximum of 12 joules of energy per coulomb of a charge that passes through it. That is the explanation that we'll be looking for. So please ensure that you note the difference between giving a definition and explaining the EMF. Very, very important. Otherwise, with all other definitions that are related to this topic, then the principle that we talked about earlier still hold. Then the formula, we know we must always write it as it appears. When you write, especially when you are asked to draw, to calculate the parallel resistance, please take the formula as it appears in the formula sheet. 1 over Rp is equals to 1 over R1 plus 1 over R2 plus 1 over R3. Let us avoid that thing of the product over the sum. Let us avoid it, please. Take the formula as it is from the formula sheet, substitute into the formula, then work out the answer. Take the formula, substitute into the formula, work out the answer, please. And then when it comes to the circuits, it is important that we identify resistors that are connected in series and resistors that are connected in parallel. And in physical sciences, we use current or movement of current to identify resistors that are parallel and resistors that are in what? In series. So before learners look at the questions, it is important that they trace the current from the positive terminal to the negative terminal. They will move from the positive terminal throughout. They look for the path that will allow the current to return to the negative terminal. They then move using that. And then as they move, they will then get to the nodes, whereby there will be two paths available for the current. And in such instances, the resistors in those paths will be the ones that will regard as resistors that are connected in what? In parallel. But if the current has got only one path and all of it will pass that path, then it means the resistors in that path that is not divided, those resistors are connected in what? In series. So we need to emphasize this point to our learners because they are doing maths. And in mathematics, they tend to think those ones that are side by side, they are parallel. So they tend to think whatever that goes side by side like that will be parallel. But then we need to explain to them that in physical sciences, that is not how it works. We look at the movement of what? Of current. Hence, the tracing of current. Before you even look at the questions, you need to trace the current from the positive terminal to the negative terminal. And then from there, you will then be able to tell, but this resistor and that resistor are in the paths that have divided the current, which means these resistors are connected in what? In series. But if you find already the current that goes through this resistor and that resistor is the same, they are in the same path from positive terminal to the negative terminal, then it means those resistors are connected in what? In series. So those, or rather, that is how we identify resistors that are connected in parallel and those that are connected in series. Very, very important that we do that. And we also check, if there is a switch and this switch is open, does that switch block the main current, meaning the total current or not? If that open switch is the main switch, meaning it blocks the total current, then it means there is no current that is going to flow because we are going to have an open circuit. And in an open circuit, the current will not be able to flow. So our learners must be able to see, okay, in this case, these things, or rather this resistor and that resistor will not be able to get the current. Because people can use switch to determine as to whether these are effective resistors or not effective resistors. Effective resistors are those that get what? That get the current. So we must be able to interpret our circuits in that way. And then we know for total resistance, it will be, in our instance, there is an internal resistance also. So it will be R external plus internal resistance. And R external is made of what? All the external resistors. That some of them may be connected in parallel and some may be connected in what? In series. And the trick will always be, start first by finding the parallel resistors or parallel combination. Calculate R parallel first so that everything it is in series, because with series, R external for series will be sum of all those resistors that are getting the same current. And then you are good to go once you have done that. And then when it comes to circuit explanation, this question comes a lot, because they will say now that the switch has opened, because they can use the switch. Remember I said in a circuit diagram, the resistors that get the current are the ones that will refer to as effective resistors. So as you trace the current, you then look or remark, will this one get the current? Will this one get the current, or that one get the current or not? Then those that get the current will say they are effective resistors. But we can then use a switch maybe in one branch of the parallel combination. And once you open that switch in one branch, it means this other one in that branch, this other resistor will no longer get current. All of the current will then pass in one branch. Then that one is rendered ineffective. It's no longer part of the circuit. Then they ask what then happens in such instances. We know whenever a resistor is added in parallel, then the total resistance of the circuit will decrease. But whenever a resistor is added in series, then the total resistance of the circuit will increase. And the opposite of that is also true. They remove a resistor, not literally removing it, but opening a switch, rendering it ineffective. So if it is now ineffective, it means that it is no longer part of the circuit. Then they have removed it in a circuit. Or rather, they take a conducting wire from one point to the other. Obviously, current as it moves, it will always look for the path of low resistance. So if there is a path of zero resistance, then it means all the current will take that path. Then it means so these other resistors will no longer get the current. Again, the aim of the current is to move from positive to negative terminal. Then we work it like that. So we must then check for what then happens to the total resistance of the circuit because of the change that was made. And then after finding out what happens to the total resistance because of the change that was made to the circuit, then we relate that change with the current. We know current and resistance, they are inversely proportional. If total resistance increases, total current decreases. And from there, because those are the main things, from there, you'll then be able to tell what will happen to the power somewhere, what will happen to the energy, what will happen to whatever that they might ask. Most importantly, find out what happens to the total resistance because of the change that is being made. And then after finding out what happens to the total resistance or R external, then you then talk to what happens to the total current. Current is the most important thing when it comes to circuits. If you can know what happens to total current, then you can be able to tell us what will happen to power. You'll then be able to tell us what will happen to energy. You'll then be able to tell us what will happen to a potential difference across that resistor. And all those things, they depend on what? They depend on what happens to the current, and current is influenced by what? By resistance. How do you change the resistance? I made an example. You can either add or remove resistor, either in parallel or in series. And many times they use a switch or they connect a conducting wire between 2 points. to render this other variable, this other resistance ineffective. So please be on the lookout for such questions. We do not want to lose marks on such questions. And we know when it comes to energy or temperature in physical sciences, we relate it to energy. So if energy increases because of an increase in current, then it means whatever resistor there will become hot. But if energy decreases because of the decrease in current, then whatever resistor there will become cold. And then that is very, very important. And then when it comes to the brightness, we relate brightness with power in physical sciences. So whatever happens to power, if power increases because of an increase in current, then that bulb will glow brighter. And the opposite of that will hold. And in the explanation, like we have been doing, we use physics formula to explain. And then if that formula has got other variables and you're comparing these two, these other variables must be kept constant. That is the principle that we use. And then lastly, we'll have cost of electricity. With cost of electricity, many of our learners tend to ignore or neglect this part of electricity. It is examinable. It might be asked. So please practice this thing of calculating cost of electricity. And the formula, it is not given in the formula sheet, but it is there. P, which is power, but the power for cost of electricity must be in kilowatt, time must be in hours, and tariff is the money that whatever service provider charges for a kilowatt hour of electricity. We use kilowatts because an hour for time, because the electricity is measured in kilowatt hour. For example, will be, I get petrol is measured in, or they use the unit of liter to measure petrol or to cost petrol. But to cost electricity, they say kilowatt hour. Hence, when we want to calculate cost of electricity, we must say, convert our power to kilowatt. We must convert our time to what? To hours. This formula is very, very important. And then you determine, remember, your time can be given in seconds, convert to hours, can be given in minutes, convert to hours. We'll be lucky if it is given in hours because you just take it and then use there. If it is given in days, you must convert those days to hours. If it's given in weeks, same. If it is given in months, if it is given in years, don't know what else, decades, centuries, and whatever, we must convert time to what? To hours, always. That is the mediation that we wanted to do with you when it comes to paper 1. Then I'll be moving to paper 2 shortly. I'll just take 1 minute breather and then continue with paper 2. Okay, just 1 minute. Okay, no, thank you very much for still being here. And now we'll look at paper 2, but most of the things we have already talked to, the principles that we talked to of answering a physical sciences paper are applicable even in paper 2. So please go through your question paper, identify questions that you can answer. And then before we get to that, please ensure that you fill in the attendance register. If you are with your teachers, please ensure that we complete the attendance register for this session. Then, when it comes to paper 2, these are the knowledge areas that we must know. 1, matter and material, organic, that is organic chemistry, 60 marks, plus or minus 60 marks. Of the paper, 150 will be on organic chemistry. And we know under organic chemistry, that is where we have IUPAC naming, that is nomenclature. And then we also have physical properties, and we also have organic reactions. Then we have chemical change. With chemical change, that is where we have rate and extent of reaction, energy and change from grade 11. We have chemical equilibrium. Look at those marks, about 34 marks from, well, will be on chemical equilibrium. We also have acids and bases, grade 11. Grade 11. And remember, grade 11 goes to the calculation of pH. So please note those things. That is our paper, 150. Then get into it. I'm not going to talk to the things that I referred to in paper 1. They are already done. Matter and material, naming and the structures. Very, very important that learners know the difference between functional groups, homologous series, and the likes. And we must know, please, we must know the functional groups of each and every homologous series. It is important, especially when you draw the structural formula. You must first, you must draw the correct functional group. If the functional group is wrong, then the whole structure becomes wrong. If you are asked to draw the structural formula of a carboxylic acid, the first thing that we will look at is the functional group of carboxylic acids. If that is wrong, then the whole thing becomes wrong. So you must know the structural formula of all the homologous series that we have. Very, very important. And then when you complete the structure, ensure that each and every carbon atom is bonded 4 times. Ensure that each and every carbon atom is bonded 4 times. Very, very important too when it comes to the drawing of the structure. When it comes to naming, we need to first identify the longest continuous carbon chain, and that will be the stem or the parent name. Identify the longest continuous carbon chain. If you can count without breaking, yes, it can take a corners there and there. As long as it does not break, then those are your what? Those are your carbons in the longest continuous carbon chain. You identify that, then that becomes your what? Your parent name or your stem. Then you will get the mark for that. And everything else, which is not part of the longest continuous carbon chain, becomes a side chain or side group. Then you put it in the name. We know if you write a formula between the name and the number, we must have a hyphen. But between a number and the number, in a case of the same side group, we put a what? A comma. And when you have more than one same side group, we know we'll di for 2, tri for 3, and tetra for 4. So those are the principles that we must have. And the sequence will be the one that the substituent that comes first alphabetically must be written first. The substituent that comes first alphabetically must be written first. And when we look for alphabetical order, we exclude the di, the tri, and the tetra. We look at the actual substituent. You look at the actual substituent. And also when it comes to naming, especially the homologous, the haloalkanes and the alkanes. After identifying the longest continuous chain and the substituent, please add the positions of all the substituents, including your halogens. You'll add them, and the numbering or the counting that is going to give you the smallest sum. The counting that is going to give you the smallest sum will be the correct numbering that we will take to name our haloalkane or an alkane. We do not prioritize the halogen. We look forward for the smallest sum. And then if we find that the sum is the same, example will be when you go to the right, when you go to the left, you find out the sum is the same. In instances such as those where the sum is the same, to break the tie, we then look at the substituents, and then the substituent that comes first alphabetically will be the one that is prioritized. So we do not prioritize based on this substituent is a halogen an alkyl group. No. We look between them, which one comes first alphabetically, and then we prioritize that one. So please note that. Or when it comes to haloalkanes and alkanes, we prioritize the sum first. We count, and then we add the positions, moving from left to right and from right to left. And the sum that is small is the one that is, or the one that gives us the smallest sum is the one that we are going to take when we name our haloalkane and alkane. But in an instance where sum is the same moving from left to right and from right to left, that is where we then break that tie, taking alphabetically which one comes first. And then the one that comes first alphabetically will be the one that is prioritized. And you should hear me well, hence I emphasize this point. Or I'm not saying you prioritize halogen. I'm saying you look at the substituent that comes first alphabetically. That is the principle that we must note. And then you number, and then you put in the hyphens, you put in the commas between the number and the name. That is very, very important. But when it comes to all other homologous series, your alcohols, your aldehydes, your ketones, and the likes, remember that you number in such a way that your functional group get the smallest number. There you prioritize the functional group. From alkenes, alkynes, alcohols, aldehydes, and esters and carboxylic acids. Even though for esters, aldehydes, and carboxylic acids, again, we do not show the position of the functional group because it will always be carbon number 1. But for these other ones, you will number your carbon atoms in the longest chain in such a way that your functional group get the smallest number. And the principle holds. If you find when numbering from left to right and right to left, your functional group is at the same position, to break the tie, you then take the numbering that will give the substituents the smallest sum. And that will be the correct number. That is what we need to note when it comes to the naming and the structures. And we know hydrocarbons of ours, we have saturated and unsaturated. We must know those things. The difference between saturated and unsaturated. We must also know the difference between the types of isomers. We have functional isomers, we have positional isomers, and we also have what? Chain isomers. We must know the difference amongst those ones. And in the definition, for all the three types of isomers, firstly, they must have the same molecular formula. That is where we start. And then depending on the type, they will differ in terms of the chain length, they will differ in terms of the position of the functional group, they will differ in terms of the functional group. That is how we deal with with the isomers. That is that when it comes to the naming of organic molecules. Then when it comes to physical properties, definitions. And we know that the physical properties that we deal with in grade 12, we have only three. That is boiling point, melting point, and what? And vapor pressure. And these three physical properties of ours, from one organic molecule to the other organic molecule, they depend on the strength of intermolecular forces. They depend on the strength of intermolecular forces. And the strength of intermolecular forces will depend on the structure or the type of the functional group. So on the structure, that is where we'll then talk to the chain length. That is where we'll talk to the degree of branching. The longer the chain length, the stronger the intermolecular forces, the higher the boiling point and the melting point, but the lower the vapor pressure. The more the branches on the molecule, the weaker the intermolecular forces, the smaller the boiling point and the melting point, but the higher the vapor pressure. That is what you need to know, and we need to be able to deal with that in that fashion. When it comes to the functional group, remember I said the physical properties depend on the strength of intermolecular forces. And the strength of intermolecular forces can be determined using the structure, and the strength can also be determined based on the type of the functional group. Because type of functional group leads to what? To type of intermolecular forces. We know the difference, or we have those with only London forces only, those with London forces and dipole forces, and those with London forces, dipole forces, and one side of hydrogen bonding, and the other one hydrogen, two sides of hydrogen bonding. So the type of functional group will then determine the type of intermolecular forces. What does that then mean? It means that if you are going to compare the physical properties of molecules that are from the same homologous series, they will obviously have the same type of functional group. They will obviously have the same type of intermolecular forces. Then to compare their physical properties, you'll then have to look at the what? At the differences in the what? In the structure. And how can the structure differ? The structure can differ in terms of the chain length or branching, degree of branching. But if you compare the physical properties of organic molecules from different homologous series, then in that case, you focus on what? You focus on the type of functional group or type of intermolecular forces. That is how we deal with these things. And this is one question where we expect each and every learner to get all the marks, because it is always there. And the expectation is always the same. So in our response, when you compare one of the physical properties, we must write this thing in a point form. The point form will be point number 1, point number 2, point number 3. Point number 1, if you compare from the same homologous series, then you must compare the structure. If they differ in terms of the chain length, then you compare the chain length of the compounds that you are referring to. If they differ in terms of the branches, amount or number of branches that they have, then you compare, you use the branching. You'll say this one has more branches than this one has longer chain length than that one. And as I explained, longer chain length means that point number 2 now, this one consists of stronger intermolecular forces than that one. Then remember, the physical properties are about the change in a state or in a phase, and that requires what? That then requires energy to break them. So it then talks to amount of energy that will be required to overcome the strength of those intermolecular forces. The ones with stronger intermolecular forces will always require more energy to overcome the strength of intermolecular forces. When you compare those that are from different homologous series, I said point number 1, or rather, first thing, we are going to use type of intermolecular forces or type of intermolecular forces to compare. Point number 1, you mentioned the type of intermolecular force that each of those that you compare consists of. You say A consists of London forces only. B, on top of London forces, it consists of dipole forces. Then point number 2, you then compare the strength of those intermolecular forces. So point number 1, we mentioned the type of intermolecular forces. Point number 2, we then compare the strength of those intermolecular forces. And then after comparing the strength of intermolecular forces, then you talk to the amount of energy that is required. That is standard. That is how we explain the differences in the physical properties. Always. Please do it like that. And then this question, there are in many cases where it will come in a form of what? In a form of investigative question. Because many a times learners are then required to compare physical. Then it will then mean your physical property in that instance will be the what? The dependent variable. Then your independent variable will be those things that affect the strength of intermolecular forces. The type of functional group or type of intermolecular forces, chain length or branching, those are possible independent variables. Where now you just have to check or report these two things that I am comparing here. How do they differ? Do they differ in terms of the type of the functional group? Or do they differ in terms of chain length? Or do they differ in terms of the branches that they have? Then that becomes your independent variable. And the difference will lead to what? To the difference in the physical property. Then the physical property in question. Because in that case, they will be saying that we are comparing the physical property of this and that, this physical property of this and that, maybe vapor pressure. Then vapor pressure becomes the dependent variable. Then you respond using that, because I said when we were discussing paper 1 that once you have your physical your variables, then you'll be able to write your investigative question, your hypothesis, and your conclusion, as discussed previously. So please be able to do those things. And then this question might also come in a form of a graph and a table. We must be able to interpret the graphs. We must be able to interpret the tables. From that table, you must tell Hore, will this be a liquid at this temperature, given this boiling point of it? Will this be a gas at this temperature, given the melting point of this, or the boiling point of that at a certain temperature? So those are some of the things that we must do. And I know this is a revision from grade 10. So please interpret using those things. That is that for physical properties. Point form, please. Point form, when we explain. Then when it comes to organic reactions, please, guys, we follow the diagram. And many of our learners struggle, especially when this diagram, when these molecules are given in a form of a condensed structural formula. My advice will always be change everything to structural formula. For me, it is easier to work with structural formulae than it is to work with any other representation of organic molecules. So before you even look at the questions, try to change everything into a structural formula. And as you change, please don't say here there is a missing carbon and then you add a carbon. No, we work with what is given. Because if there is one thing that many of our learners miss is, if from one reactant to other product, you find that the number of carbons are no longer the same, they tend to say, no, this question might be wrong somehow. No, if that is the case, then it means cracking has taken place there. It is not a mistake. So please draw, or rather convert everything into structural formula as given. Then follow the arrows. Follow the arrows. We have those things that we use. I don't know kind of what is the name of this kind of mnemonics or what. I'm not sure of the name, but we have those triple S. When you move with the arrow from a saturated to a saturated, then the type of reaction is substitution. When you move from a saturated, meaning single bonds between carbon atoms, to unsaturated, we know the type of reaction is elimination. And then when you move from unsaturated, meaning double bond somewhere, to saturated, we know it is addition. Again, we have triple S, we have SU, we have USA. Please use that. At least we must not get the main type of reaction wrong. And then if you apply that correctly, at least when it comes to identifying the type of reaction that is taking place, you'll never go wrong. Because you'll know, okay, This one, single bonds between carbon atoms. This one is also single bonds between carbon atoms. Therefore, this type of reaction here is substitution. This one, we have single bonds between carbon atoms, but following the arrow, it leads to double bonds between carbon atoms. Then it means it is an elimination reaction. This one, from a double bond between carbon atoms to single bonds only, then it means it is an addition reaction. At least the main type of reaction you must get. And then if you apply that thing correctly, I'm telling you, you will never go wrong. Then we can then talk to the type of the reaction after at least identifying as to whether it is elimination, substitution, or addition. Those are the main type of reactions. And then the specific will then depend on what is being eliminated, on what is being added, and what is being replaced in the substitution reaction. Then you go from there. But let us identify the main type first using the triple S, USA, and SU. I'm telling you, you'll never go wrong. And I know you are aware of those things. Practice and practice and practice. Then there is this thing of the saturation test. And it is a test, it is a practical that we must do in our schools. So please, whenever you are asked to give the observation, you must talk to what we will see during an investigation or during a practical. And we must then say, or the solution will become colorless or decolorizes. Don't say there is color change. Color change from where to where? You must be specific and tell us, or this one becomes colorless because we know bromine water is brown, then it will move from brown to colorless and the likes. So please talk to the exact observation that is made during what? During a practical. That thing is very, very important. And know the reaction conditions for all the reactions that we have. Know the reaction conditions, please. Each and every reaction has got, not all maybe, but many of our reactions have got their organic, their conditions. And it is those conditions that will tell, or in this instance, this haloalkane will undergo substitution. In this instance, this haloalkane will undergo elimination. And we know, or the products that we'll get for elimination reaction is what? Is an organic product, which will be an alkene, a salt, and what? And water. Based on what? On the reaction conditions, which are concentrated strong base and heat. But if we have dilute strong base and mild heat, then we know in that case, we'll have a substitution reaction. So please know those reaction conditions, because they talk and they will then help you to identify the products that are there in a reaction. Then when we go to chemical change, the rate and extent, energy and change from grade 11. Those things of exothermic and endothermic reaction graphs. And we know from those graphs, we must be able to tell the energy of the reactants, energy of the products, energy of the activated complex, and we must be able to give the enthalpy change, delta H. We must be able to give the activation energy. That is for forward reaction. And also we must do that for reverse reaction. Remember, the activation energy of the reverse will not be the same as activation energy of the forward reaction. We must be able to give that, as you saw, plus or minus 10 marks will be coming on from there. So we must know those things. They are very, very important. Interpretation of those graphs, very, very important. Let us look at those things. Then when it comes to rate of reaction, maybe before we get to rate of reaction, I get an interpretation of those energy profile graphs of our reactions. Calculations may be asked there. You may be asked to calculate enthalpy change based on the graph. You may be asked to calculate activation energy of the reverse reaction based on the graph, or energy of the activated complex based on the graph. So those calculations are also important. We must know all those things. Then when it comes to rate of reaction, definition is very, very important. State the definition. I know in our examination guideline, the definition says the change in the concentration of product or reactants per unit time. That is given, well and okay. But there are instances and there is a possibility because we have different mechanisms that we use to find the rate of reaction. Some people will use changes in mass to find the rate of reaction. Some people will use changes in the volume of something to find the rate of reaction. Some will use changes in moles, some will use changes in concentration. So you must then be careful because a question might want you to be specific to what is being measured in the particular reaction. I'm saying we have mechanisms, different ways that we use to identify or define or determine the rate of reaction. Then you must know, okay, or if we are then asked to give a specific definition of rate of reaction, we then have to focus on what is being measured in that particular reaction. If they are measuring changes in mass, then your definition must be based on changes in what? In mass. Change in mass of the contents per unit time. If time is in seconds, then you become specific to seconds. If you are told, or we are collecting the volume of carbon dioxide in this reaction, then then they want you to be specific in the definition. They will say, give the definition of rate of reaction in this. You see, they are now being specific. They are not looking for the general definition from examination guideline. In cases such as those, then you look at what is being measured in that particular reaction. If they are measuring changes in volume of carbon dioxide, then your definition will be change in volume of carbon dioxide per second if the time that they are using there is seconds. So just be careful, or now what is it that is being used to measure the rate of reaction. And also, you must know the apparatus that they use. Again, if they are looking at the changes in mass, obviously mass scale must be there. You must be able to identify mass scale. Remember the list of apparatus that we talked to. If they are looking, they are measuring, they are collecting the gas, we have gas range that is used to collect the gas of the product. Remember the apparatus that we talked to. So we must know all these things so that we are able to respond to a question where we'll be asked to identify the apparatus used in the experiment. Those are things, those things are very, very important that we know. And then also the graphs that shows the changes in the amounts of your reagents during a reaction, very, very important. We know for a reactant, the graph will start from the top because you start your reaction with the what? With the reactant. And then it will go down, 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 down. But for a reactant, because at the beginning of your reaction, you do not have the product. So it means, or the graph that will show the changes in the amount of the product against time will start from 0 and it continues up, 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 up until the end of the reaction. Then how will you know, Hore, for a reactant and for a product that the reaction has reached completion? If the reactant that you are dealing with is a limiting reactant, it will go down up until 0. If it reaches 0, it reaches 0. That is a limiting reactant, of course. Then it means the reaction has reached what? Completion. An excess reactant, we know at the end of the reaction, some of it will still be left. Then it will go down, go down, go down, go down. And then at some point, it will then be straight horizontal. There won't be any change in its amount. Then it means at the point where it started to be constant, then it means that is where the reaction reached completion. And for a product, it will go up, 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 up until a point where the amount of the product does not change, remains constant. At that point where it starts to be constant, that is where we say our reaction has reached completion at this point. So we must be able to show these changes. in the amount of your reactants and product against what? Against time as a reaction proceeds. So it will be for reactants, they will start at the top going down, and you must differentiate between a limiting reactant and an excess reactant. And for your product, it will start from 0, it goes up. But these changes, we must be careful. They will not take a form of a straight line. They must curve-like, be a curve-like, and show that changes. I'm going to explain why do we say that. Because if you look at this and the mechanisms that I've referred to just now, you look at the graph and the mechanisms, it means that we can be able to calculate the rate of reaction using changes in mass over time. We can be able to use changes in volume over time, changes in concentration, or changes in number of moles. Then it means for a graph of amount versus time, gradient of that graph will be equal to the rate of reaction. And because at the beginning of the reaction, the rate of reaction is at its highest, but towards the end or towards completion of a reaction, the concentration or the amount of the reactants has decreased. Then it means the rate of reaction will do what? Will decrease. Hence, you will see that they will not move with the constant gradient. They must change a band like that, showing the decrease in the rate of reaction. And decrease on the rate of reaction is because of what? Because the rate decreases as we move towards what? Towards completion. We know at completion, the rate of reaction is equal to 0. So it will be highest at the beginning, and then it will then decrease. As it decreases, then the stiffness also decreases, stiffness also decreases, stiffness also decreases up until the end. That shape is very, very important. It can't be straight line. So even when you draw and you show those changes, we must see that decrease. And that decrease, we look at it in terms of what? Of the steepness. So the steepness will start with being steeper with a high gradient, high rate of reaction, then the steepness decreases, steepness decreases, steepness decreases, steepness decreases, steepness decreases until it becomes horizontal. So please draw your graphs or show those changes in that way. Very, very important that we do it like that. And then we then have to interpret the graph, and then we calculate the rate of reaction. Remember, we talk of average rate of reaction. Eh? When you talk average rate of reaction, so it says final minus initial. So we must, even if it is 0, we must substitute those zeros. And for reactants, because they are decreasing as reaction starts, then the formula will be minus change in amount over change in time. Accurate amount can be concentration, can be number of moles, can be volume, can be mass. So it starts with a minus because your it goes down, their gradient is negative. And then for product, because they increase as reaction proceeds, then it means so now they will go up. The formula will be plus change in amount over change in what? Change in time. So the gradient we have now established, or it represents the rate of reaction. So when you calculate that gradient, that will be the same as calculating the rate of reaction when you are given a what? A graph. That is very, very important. But in the case of an open system reaction, whatever that will be living there will be the gas. Because sometimes you may be asked, or what is responsible for the decrease in mass? If it is an open system and you see, or we have a gas as a product, then it means that gas is responsible for changes in mass. We told, oh, the mass of the contents decreases as reaction proceeds. It means it is that gas that is what? That is escaping the system. So we must be able to respond to such practical questions. And it's very, very important that we understand. So the practical questions are very, very important. Sometimes we have this one, sodium thiosulfate, and it is an experiment also that we use to determine the effect of concentration on the rate of reaction. And then for sodium thiosulfate, we'll have a sulfur forming as a solid there. And then you put it on the cross. Obviously, the cross will fade away because of what? Because of the formation of sulfur, which is a solid. A solid will cover everything. So such questions we must be able to respond to because they are investigative questions. And with rates, we have a lot of experiments that we must perform. If we are unable to do it, let us at least view videos of this experiment, please. We must be exposed to those formulas. Then once we have identified the rate of reaction, we have factors that affect the rate of reaction. And all those factors are important to understand. We have nature of reactants. It can affect the rate of reaction. But as a person who's conducting an experiment, we can't change the nature of reactants. What we can change is maybe moving from one reactant to the other reactant. Again, obviously, the two reactants will have different properties. You might find out this one is more reactive than the other one, and then that will then affect the rate of reaction. So those things are things that we must note. But nature of reactants can affect the rate of reaction. But you can't, when you are asked, how can you increase the rate of reaction here for the specific product that you want to form? You can't say, I'll change the reactivity of this. No. Those things we can't do. The only way we can change the nature of reactant is by using a different reactant. Then we have temperature that talks to the average kinetic energy of the particles. Then we have concentration. We have the frequency of collisions there, and concentration works the same way as the pressure because now you'll be having more particles in a given volume. We have a catalyst which provides an alternative pathway of lower activation energy, and then we have surface area that talks to the exposure of particles to react. We must know and be able to apply. Or now, when we do this, when we increase this, what will happen to the rate of reaction? Remember all these changes for us to be able to increase the rate of reaction. All these changes must be done in the reactant. Again, we want to increase the rate of reaction to make the products fast. You can't change anything in the products, but you change the conditions in the reactant. You change the concentration of a reactant. You change the temperature in the reactants. You change for the reactants. You might not be able to change for it specifically, but it will influence the reactants. We change the surface area in the reactants. And we must be specific, especially when it comes to concentration and surface area. Surface area that we can change, it is the surface area of the solid reactant only. And you can't say, I will increase the surface area. To us, it's the same as not saying anything. It must be, I will increase the surface area of a solid reactant. I will increase the concentration of an aqueous or solution reactant or a gaseous reactant. Then you are specific because with concentration, we talk to solutions. Those are aqueous solution and the gases. And then for surface area, you become specific to the solid reactants. But these other ones, so now you can just be general because they will influence the whole thing in some instances. So please be careful on how to do these things. And as I indicated earlier, for these changes we might be required to show their effect on the graph. Question will come and say, redraw the graph and show how the graph changes when temperature is increased. We know once we increase temperature, the rate of reaction will increase. Then show that change on the graph. Steepness, it means the steepness must increase. And the time it takes to reach the completion must be small. Those are some of the things that we must be able to do. They say they have added a catalyst, then tell a suitable catalyst, then show us on the graph, how will the graph now of that product against time change? Then the graph will be more steeper. The graph will be more steeper, but it ends at the same level. Remember, the amount of the product that will form will still be the same. The only difference is that to get to that amount, it will take us a shorter time. The only time where the amount changes, it is when a limiting reactant amount has been changed. If they change the amount of the limiting reactant, and it's important that we are also careful. Here it is the limiting reactant that can determine the amount of the product. Then the changes in the amount of the limiting reactant will be the one that will then determine the amount of product that will form. If they change the amount of the excess reactant, that will not have any effect on the amount of the product. The amount of the product is influenced by what? Is influenced by amount of the limiting reactant. So we also need to be careful of that. But I wanted to highlight for the changes in the rate of reaction, we must also show on the what? On the graph. Even if we are given a graph to interpret, then you are asked which one is taking place at a higher rate. The one that is more steeper will be the one that is closer to the y-axis. Okay? So the one that is more steeper will be the one that represents a reaction that takes place at a higher rate. So we must be able, because they will say, refer to the graph to explain or to identify the reaction that is taking place at a higher rate. You'll say this one is more steeper than this one. Therefore, this one takes place at a higher rate. Maybe this one is taking place at a higher temperature, or the concentration of the solution there is higher than this one, or they have added a catalyst, or they have used a higher surface area in their reactants. Those are things that we must be able to do. But whenever they ask you to refer to the what? To the graph, please talk to the gradient or the steepness. But this one is more steeper than this one. You can see from the graph, but this one is closer to the y-axis than this one. And then, but you don't say it's closer to the y-axis. That is not the language we use. We say it is more steeper. Maybe let me stick to that, because some people will go on and write, or this one is closer to the y-axis and not get it right. You say it is more steeper because you need to talk to gradient, or it has a higher gradient than this one. Accurate gradient is the one that is equal to the rate of reaction. And then therefore, the one that is steeper is the one that is occurring at the higher rate. Higher rate will be a result of higher temperature, higher concentration, higher surface area, addition of a suitable catalyst. Those are some of the things that we must be able to do. Then it comes to, for a reaction to take place, we know the particles must collide, but not all collisions lead to a reaction. Particles must collide effectively. That is where now collision theory comes in. Collision theory talks to the frequency of what? Of effective collisions. Yes, particles must first collide, but they must collide effectively for a reaction to take place. And for particles to collide effectively, we have two conditions. Particles must have correct orientation. Particles must have sufficient kinetic energy for them to collide effectively, and then we will have a what? A chemical reaction. That is where we start. But if you want to increase the rate of reaction, then learners must understand you must have more of these effective collisions. That is when the issue of us increasing comes in. For a rate of reaction to increase, we must have more effective collisions. Reaction has already started, but we want for it to take place at a higher rate. Then it means we must increase both temperature, we must increase surface area, we must increase concentration, we must add a suitable catalyst. That is where now collision theory comes in. Collision theory explains to us how a reaction takes place and how we can increase the rate of reaction. How so? We need effective collisions, one, for a reaction to start. But if we want it to take place at a higher rate, we must have more effective collisions. That is basically what collision theory deals with. Then, when we then explain how these different factors influence the rate of reaction, remember, rate of reaction, we must end up with what? With more effective collisions per unit time if we want to increase the rate of reaction. So you'll talk to temperature, we'll talk to surface area, we'll talk to the concentration, talk to addition of a catalyst. And then when you explain using collision theory, always place 3 points. Then you talk to the effect of each one in the first point. Then the second point must talk to the influence of each one on the two conditions that I referred to. That one of correct orientation, or this one changes what the kinetic energy of the particles. You'll either have more particles with correct orientation, or you'll have more particles with sufficient kinetic energy. And more particles with correct orientation or more particles with sufficient kinetic energy will lead to the last point, which is what? More effective collisions per unit time. So whenever we are learners are asked to explain using collision theory, the last point there must be more effective collisions per unit time. That is, if that factor has been increased. But if that factor has been decreased, then it will be less effective collisions per unit time. Then the second point has to talk to the two conditions of effective collisions, either the correct orientation or sufficient kinetic energy. Our learners must know that. And then the first point will then differ depending on the factor that we are changing. That is very, very important. And also this question may come in the form of an investigative question. If it comes in the form of investigative question, it then means the factors that affect the rate of reaction are your independent variable. So the factor from one experiment to the other experiment, because you'll be comparing the rate of reaction of the two experiments. Then the factor that is different, the factor that affects the rate of reaction and is different from one experiment to the other experiment, will be the independent variable. And then rate of reaction will be the dependent variable. And then, as we have explained earlier, then you'll be able to write those conclusions, hypothesis, and investigative question. Those are things that we must be able to deal with. And then when it comes to chemical equilibrium, one, for a reaction to reach equilibrium, remember in the rate of reaction, we are talking about an open system. So for a reaction to reach equilibrium, it must take place in a closed system, and the reaction must be a reversible reaction. Those conditions are important. You must note that. And then you must be able to apply Le Chatelier's principle. Or rather, we have three factors that then affect the rate of reaction. But before we get to that, what then happens to the rate of at equilibrium? Said for a reaction to reach equilibrium, two conditions first must be met. The reaction must be reversible, and a reaction must take place in a closed system. And once a reaction reaches equilibrium, what then happens? At equilibrium, the reaction has not stopped, but the rate of the forward reaction is equal to the rate of the reverse reaction. And the concentration of the reactants and the products remain constant. They have not been used up. They are there, but they are not changing. So those are the two conditions that learners must note, because that will then help with the interpretation of the graphs. So those are things that we need to note. And then once a reaction is at equilibrium, that reaction can be disturbed from equilibrium. That is where now Le Chatelier's principle comes in. Once a reaction reaches equilibrium, it wants to stay at equilibrium. So whatever disturbance that is imposed on it, then the reaction will oppose that disturbance. And there are three things that can affect or influence equilibrium, state of equilibrium. We have concentration, we have pressure, and we have temperature. Those are the three things or disturbances that can influence the rate of, not the rate, but the state of equilibrium. So whenever any of this is imposed, change is imposed on equilibrium, then our equilibrium will then oppose that change. So even here, with the response of the reaction, one, we must identify the disturbance. Two, talk to the response of the reaction. Three, talk to the reaction that is favored. And then number four, talk to the implications. What are the implications? Implications are what will then happen to the amount of the reactants and the products. For instance, let's say temperature has been increased. What will the system do? The system will decrease temperature by favoring endothermic reaction, because it is the one that absorbs heat. Okay. Which reaction is that? Forward reaction is favored, as an example. Then what are the implications? Implications are product of the forward reaction will increase, the amount of them will increase, and reactants of the forward reaction, the amounts of them will decrease. That is, or those are the implications that we should always refer to. And then they will then be able to help us to talk to the changes in the graph and changes in the question. Maybe we may be asked to do it. That is very, very important. And then if this is then given in a form of a graph, we must then be able to identify here the disturbance is this, here the disturbance is this. So we can have a graph of amount versus time and a graph of rate versus time. So obviously the reaction, as we have talked about it, about the graphs in the rates of reaction. Take those three graphs that I talked about and then put them in one axis. That is basically what happens for amount. The only thing here is that the amount of the limiting reactant does not reach zero, otherwise the reaction will stop. Here, because we are dealing with a closed system, none of the reagents will reach zero. Then product will increase, the reactants will decrease up until the point of equilibrium. How will you know a reaction has reached equilibrium? Once all the products and reactants remain constant. Once they become constant, for that period when they are constant, it means the rate of the reaction has reached what? Equilibrium. So from the moment they start to be constant, then you know that is the point where the reaction reached equilibrium. Then the equilibrium will last for a certain period. Then there will be a disturbance. If you see one of them increasing, especially a gas or a solution, maybe it goes up, it should spike up or spikes down, then you know if only one does that at a particular time, then you know the disturbance there is the disturbance in what? In concentration. If it goes up, its concentration has been increased. If it goes down, its concentration has been decreased. That is how equilibrium has been disturbed. Then you apply Le Chatelier's principle because the system will want to go back to reinstate what? Equilibrium. If all of them, they spike either up or down, especially the gases, this will be the case for gases, then you know the disturbance there, it is the disturbance in what? In pressure. If they all go up, if all your gases go up, then you know the disturbance there is an increase in pressure. If all of them, they spike down, then we know the disturbance there, it is the disturbance in what? In the decrease in pressure. And then if there is none that is going up or down, but you can see after this time, moving forward, they are no longer constant, and then they will start to be constant after some time. So if there is no spiking up, but there are changes thereafter, then you know the disturbance is the disturbance in what? In temperature. Then you must check or not. Which one increased? The one that has increased, it means it is the product of the reaction that was favored. Then you look at your delta H, because delta H will tell you or if it is positive, it is endothermic reaction, it is favored by an increase in temperature. If it is negative, then it is exothermic, it is then favored by a decrease in what? In temperature. Then you use that to identify the reaction that was favored, and then go on to say, okay, in this instance, it means temperature was decreased. In this instance, it means temperature was decreased. You then look at it in that way. But in the explanation, please use the 4-point method that I've explained. Then the issue comes to what? To rate versus time. Same. So when you show the relationship in the graph here, rate against time, obviously at the beginning of the reaction, we will not have a reverse reaction. So reverse reaction will start from 0 and then it goes up. And then the rate of forward reaction, you know, will start at the top because you start the reaction with reactants. Concentration of the reactants will be high. Therefore, the rate of the reactant, the rate of the forward reaction will be high because its reactants are still high in the amount. Then it goes down as they get used. And then this one, its rate increases because now the product are forming the reverse reaction. And remember, the products of the forward reaction are the reactants of the reverse. Hence, the reverse starts slow, or it starts from the bottom and then goes up. That one, starts from the top, it goes down until a point of equilibrium. We said one of the conditions, again, we said of equilibrium, the concentrations remain constant and the rate of both forward and reverse, they are equal at that point. Then you'll see them equal like that. Then at the point where they start to be equal, that is where we say now the reaction has reached what? Equilibrium. And obviously, before the first equilibrium, the rate of the forward will always be higher than the rate of reverse, before the first equilibrium. Then what happens after the first equilibrium will then depend on the disturbance. Then you'll see instances whereby both rates increase. Then once we see both rates increasing or decreasing, then you must know it is either the disturbance in temperature or disturbance in pressure. But because here we have Le Chatelier's principle, in as much as they both increase, one will increase more and the other one will increase less. The one that increases more is the one that was favored by that disturbance. If they go down, both of them, the one that decreases less is the one that is favored. Very, very important. When they go up, the one that goes up more is favored. When they both go down, the one that goes down less is the one that is favored. But I think logic dictates in that instance. You can't be favored and decrease more. The one that is favored will decrease less because it is favored. The one that is favored when they go up, it will increase more. And then possibly once they move together at the beginning, it means chances are it's either temperature or pressure, and increase or decrease. If they go up, it was increased. If they go down, it was decreased. And you move from there. But if you see a spike in one of the rates and the other one doesn't have that sharp spike, then you know the disturbance there, it is a disturbance in what? In concentration. So that is at least what you must know. And then from there, or after identifying which one is favored, then you can then go to your reaction and check, okay, for this to be favored, it means temperature must have been increased, or for this to be favored, according to Le Chatelier's principle, it means the number of moles must have decreased and all those things. Then you are able to respond to this question. That is very, very important. And then you talk to equilibrium constant. Firstly, you must know the importance of equilibrium constant. Equilibrium constant 1, it gives us the ratio of concentration of products and reactants at equilibrium. So how do they compare? Do we have more of this or more of that? Remember, in industry, we want to form more products. Then when you do a calculation of reagents at equilibrium, then equilibrium constant will then help you to identify, at this equilibrium, you have more of this instead of that. When you want the product, then do this changes, disturb this equilibrium so that this reaction favors forward reaction. So we must know that. Then it means, if Kc is greater than 1, if Kc is greater than 1, it means that we have more of the products than reactants at equilibrium. If Kc is less than 1, it means at that equilibrium, we have more of reactants than products. Then as a chemist, you'll then have to do something because you want to form more products. You want to form more products. Then that is then the importance of Kc. So the value of Kc has got its significance because it tells us, or at that particular equilibrium, what do you have in higher quantity? Do you have more reactants than products, or do you have more products than reactants, or reactants than products, and vice versa? So please, that is the significance of what? Of a Kc. Then to calculate the equilibrium constant, the name says equilibrium constant. It means that we use concentrations at what? At equilibrium. Then when you write, or rather when you do the calculation, we do not use this formula, Kc is equal to concentration of products over, no. You substitute the direct reactants and products. Don't write products over reactants. Give us those products. Ammonia over nitrogen and hydrogen. And we know when we write the Kc expression, one, we use square brackets because we are dealing with concentrations, and the coefficients of our reagents becomes the superscript, the powers there. If it is balanced by 2, then it will be 2. If it is balanced by 3, it will be 3. If it is not, or it is balanced by 1, it will be 1 like that. So don't write this. There's no mark for writing this. You must write the specific the specific expression using the real reactants and products that you are giving in your reaction. That is very, very important to do. And then we must also understand, or it is only one factor that can affect the value of equilibrium constant, that is temperature. And its effect, because the common mistake that many learners do is they think, or when temperature increases, then Kc increases. That you must erase in your head. We apply Le Chatelier's principle and check whether that change in temperature favors forward reaction or reverse reaction. If that change in temperature favors forward reaction, then Kc will increase. If that change in temperature favors reverse reaction, then Kc will decrease. You look at your Kc expression and then check, or now will this change favor forward reaction? Remember the implication that we talked about when applying Le Chatelier's principle. If the forward reaction is favored, then it means we'll have more products. And with more products, it means our Kc will do what? Will increase, because products get it in numerator. And we know when numerator increases, then the value of Kc will decrease. But if we will have more reactants, then Kc will decrease. These are some of the things that you must be aware of when it comes to the Kc expression. Lastly, acids and bases, grade 11, please. It is also there. And can't say we don't have time. We did this in grade 11. Everything that we did in acids and bases, those definitions, I know we have a lot of definitions here. We must know all those definitions. We know we have two theories that we use to define an acid and a base. We must know the definitions. Use the Arrhenius and Lorentz theory. We must know the difference between strong acid and a weak acid, strong base and a weak base. And we know that the definition does not end where we say it ionizes completely or dissociates completely. It must go on to say to form high concentration of hydronium ion or hydroxide ion. That full definition as given in the examination guideline is very, very important. Then from there, you must be able to give the conjugate acid-base pairs. We know when you have an acid, it will have a conjugate acid, conjugate base. And the difference between the two must be one hydrogen, one proton. When you have a base, it will have a conjugate acid. The difference must be one hydrogen. Those things are very, very important. And also, you must have acid reactions. Those acid reactions where an acid reacts with a metal, it gives you salt and hydrogen. Acid reacts with metal oxide, it gives you salt and water. Acid reacts with metal hydroxide, it gives you salt and water. Acid reacts with metal carbonate, it gives you salt, water, and carbon dioxide. Those type of reactions are important because sometimes this will be given in weights, and then you'll be asked to write the balanced equation. They'll just say calcium carbonate reacts with hydrochloric acid to form products. Then the first question comes and say down the complete balanced equation for the reaction that takes place. You must know the reactions of acids and balance them. Then once you are able to balance them, then you must, from conjugate acid-base pairs, we must know what an ampholyte is, and we must show how a substance acts as an ampholyte. In one reaction, it will act as a base. In another reaction, it will act as a what? As an acid. If you are given different reactions and then you are asked to identify an ampollite, you must base your answer to the given reactions. The one that shows the amphiprotic properties in the reactions given will be the one that is identified, because the question will not be about the examples. They will want you to give from the given reaction. And you check, okay, in reaction 1, but water acts as a base. But in reaction 2, water acts as an acid, which means in the given reaction, water shows the amphiprotic properties. Therefore, it is the one from the reactions that's an ampollite. Those are some of the things that we need to be aware of. Then when it comes to acids, okay, before acids, we must then be able to do pH calculations. And pH calculations talk to the concentration of the hydronium ion assemblies, not the presentation, the concentration of hydroxide ion. You look at the formula sheet. If we do not have pH, it means that we are then expected to use pH being equal to negative log of the concentration of hydronium ion. So if you have a base, we then have to use that base to form there to find hydroxide ion. That is where the issue of the types of acids comes in. Again, we have monoprotic acid, diprotic acid, and polyprotic acids. Then you then need to move from the fact that this one can form or give us one hydronium ion, this one can give us 2, this one can give us 3, and the likes. If we are given a base, we have that auto-ionization, where we'll have concentration of hydronium ion multiplied by concentration of hydroxide ion being equal to 1 times 10 to the power negative 14 at what? At 25 degrees Celsius at room temperature. We have that formula. So it then means if you are given a base, then you'll have to use that base to find the hydroxide ion. And then with the hydroxide ion, you'll then go to that formula to find the hydronium ion so that you can calculate the pH of the solution. That is how we are supposed to do it. So please practice these things of pH by concentrating on the calculation of pH directly using pH is equal to negative log hydronium ion. And then you do it like that. And then sometimes they might ask you to calculate the pH, in fact, not the pH, the concentration of hydronium ion, having given you the pH. We know the logarithm rules. In that case, we know it will be concentration of hydronium will be 10 times negative log, and negative the pH, if you rearrange using the pH, the logarithms rules. So those are some of the things that you must be aware of. And then we have stoichiometric calculations. Let us know what is the endpoint. Let us know what is neutralization reaction. We must know all those things. Or what happens at the endpoint, happens at the equivalence point. Those titration calculations are important. And the limiting reagent and the excess reactant then becomes very, very important. But stoichiometric calculations, especially in cases such as this one, we know it is always about using what you have to find what you do not have. Using what you have to find what you do not have. Those are the possible calculations that you must expect. But accident-based calculations, they are there. We needed to show you all these things. And I think that will be it from my side. Thank you very much for being here up to this point. I hope you have signed the attendance register, and good luck for both paper 1 and paper 2 until we meet again. That is where we will end with our meeting. Thank you very much, and bye-bye.